Hello, good morning. This is Physics with Keith. It's Saturday at 10 a.m. and this is your online tutorial session. I've got my phone in front of me, so if you send messages to me, I'm going to get those live and I can respond to them in real time. I've got a bunch of things lined up to cover today because I've had a few questions come in. Sorry, I just needed a drink. I've had a few questions come in. One person said they want to talk about radiation, radioactivity, and I'm happy to do that. Remember, you can interact with this live. This is a live tutorial session, so if there's something you don't understand, or something I'm saying and you say, oh no, go back over that again, or even if it's unrelated to this topic, if it's something completely different, then what you need to do is drop a message. You can do that straight into the YouTube live chat, and I get a little notice on my phone that I can respond to. Or, alternatively, you can send it through on the Facebook Messenger if you'd rather do it in a way where other people can't see. Don't know why you might want to do that. Maybe you want to ask a question and you're embarrassed by it. You know, there's no reason for that. But if that is the case, please don't worry. You can send it to me privately through Facebook Messenger. And for details for how to do that, there's a link I think attached at the bottom of this video in the description that you can click on, so you can send me messages on Facebook Messenger. So that's the introduction bit finished. Let's get started. The question was about radioactivity, and the starting point for anything to do with radioactivity is the nature of random decay. So let's just switch this over. So hopefully now you can see on your screen that I've got a little simulation here. A quick plug. Oh, good morning. Hello, I've got a message come through. Good morning to Finley. Hello, Finley. Yes, I'm very pleased that Dr. John Nunn from the National Physical Laboratory gave me permission to use these simulations in my video, as long as I give his vplab.com website a bit of a plug. The simulations are free to use, but you need a license to use them, which is why I was so happy that he said I could use them and broadcast me using his simulations in my videos. So that's the plug finished. I don't know him personally, but he's obviously a very kind fellow. So here's the simulation. I'm just going to talk you through it a little bit. On the left here, we've got a panel, and it's got, I think it's 10 by 10, it could be 20 by 20, little squares. And each little square can be either black or it can be white. Now, when I press go, they're all going to start being white. And each one has a chance, within one instant in time, of turning black. And once it's turned black, it'll stay black. It's decayed. That's what that colour indicates. So it's white, it's undecayed, it turns black, it's decayed. And as I say, each square has the same probability. And you may have done in school a sort of a model of this where you roll dice, and you have 100 dice. And when you roll them, anytime a dice is, pick a number, 6. Every time a dice is 6, you remove it, and then you roll all the ones that are left, and you count how many dice each time, and you plot a graph, and so on. This simulation is going to do the same thing. Have you seen this simulation before? Just leave a comment if you have. If you haven't, then this is quite good. It's your first chance seeing it. If you've never seen this before, then I can spend a little bit more time perhaps going through it. And so, okay, that's the plan. Now, there's two things here, and in exams, especially at GCSE level, they will often give a 2-mark question that will say something like, what do we mean by random decay? Or it will say the dice rolling practical. In what ways is that a good model for radioactive decay? No, you haven't seen it. Okay, that's super. Remember, sorry, there's a 7-second delay between you typing something and me seeing it, but that's great. So you've not seen it before. This is good. This is the first time. So the 2 marks in that sort of question, the 2 key ideas is that firstly, you don't know when a particular atom is going to, a particular nucleus of an atom is going to decay. And the second point is, you don't know which nucleus of an atom is going to decay next. So those are the two ideas. And so to emphasize that, on this little simulation, we've got a green box around one of the little cells, one of these squares. And we don't know when that one is going to decay. And we can't predict which one's going to decay next. Now, I'm going to leave the decay rate here nice and high so that we're not going to spend ages watching this happen. But on the right-hand side, we're going to have a graph. And this is going to show how many of these cells has not decayed yet, is undecayed. And then time is going to be on the x-axis. And let's imagine the time between each time we count them is a millisecond. It's probably going to be more like 100 milliseconds, but let's just say it's a millisecond. And so every millisecond, the computer counts how many squares are undecayed and plots a point on that graph. And then it does it again and plots a point on that graph and does it again and plots a point, and so on and so on and so on. And each square has the same probability of decaying in that millisecond. Okay, remember you can ask me questions if I'm going too fast. It's quite difficult without the face-to-face feedback to see if, you know, I don't get the quizzical look of, huh, when someone isn't understanding what I'm saying. That's the downside to doing things online. So if you need to do a virtual, huh, if you don't understand what I'm saying, somehow. There's no point if you're not following, you sitting there going, oh, yes, yes, but nothing's going in. So if you don't follow, if I'm going too fast, please tell me to slow down or stop or re-explain something again. So I'm going to press go. Let's watch what happens. Bang. So it starts white, and then each cell at random is going to go black. And as you can see here, the green one, the one that's got a green square around it, has not yet decayed. And we can't predict when it's going to decay. It's got a chance of decay, but we can't predict when it's going to decay. Now, at first, it kind of looks like this line is a straight line. When you glance at it, you think, oh yeah, that looks like a straight line. But then the longer you watch, the more you'll notice that it's curving. And that's green. That green highlighted cell still hasn't decayed yet. It's curving. Now, when you had more cells that were undecayed, because each cell had the same chance of decaying, more of them will decay in that time step. And there's a little analogy we can use. The dice one is a good one. If I've got 1,000,000 dice and I roll them all, I'm going to expect to get more sixes than if I have 6 dice and I roll them all. If I've got 6 dice and I roll them all, you might think to yourself, okay, well, each dice has a 1 in 6 chance of being a 6. Maybe I'll get 1 6. But let's say I've got 6,000,000 dice and I roll them all. You might think, well, maybe I'll get 1,000,000 sixes. And so when I've got more undecayed nuclei, the chance... well, not the chance. When I've got more undecayed nuclei, the number of them that will decay in a time interval is higher. And so if you look at this graph, what do you think the gradient of this graph represents? A quick reminder, in case you've forgotten, gradient is the slope, and that is the change in the y-axis value divided by the change in the x-axis value. I mean, this graph here, do you think the gradient is increasing or decreasing? Now just wait, I'll let you pop your answer there. Do you think the gradient is increasing or decreasing? Seven-second awkward silence while I wait for an answer. It seems to be decreasing. Yeah, the magnitude of the gradient is definitely decreasing. And we could be pedantic and say, well, it's becoming less negative because it's a negative gradient. This is GCSE level. We don't need to worry about that. The magnitude of that gradient, the size of that gradient is definitely decreasing. Yes, well done. Now, the gradient represents the change in the undecayed material divided by the time. We call that the decay rate. And so over time, what is happening to the decay rate? It's reducing. And what's happening to the amount of undecayed material? And we can measure that amount as a mass or as a number of nuclei. So what's happening to it? It's reducing. And it's reducing via this curve. That curve, I need to make sure I've got the curve going the right way in my camera because it mirrors things. Is it from up there down to there? There we go. That curve is what we call an exponential decay. So I will write some of this up on the board in a second. But that's an exponential decay. We'll get rid of that simulation now, and let's have a look at another one. So here's another one. This one you can get and you can use freely. You don't need to pay for this or anything, so I don't need to plug this. There's no license needed. This is a FET simulation. It came from this website here, the Colorado simulations. If you just give me a clue, have you seen these before, these sorts of simulations? You'll recognize the logo, the FET logo, if you've seen them before. And if you haven't, you can watch the video back later, and you can just type in FET into Google, and it'll give you these, and you can download them yourself and use them. I've seen that one when I was working on a different topic. Oh, super. So you may not have seen the radioactivity, it was called Radioactive Dating Game one. So the radioactive dating game simulation, it's got a bit of a naff name perhaps, but here it is. And what you can do is you can, there's 4 tabs along the top, and we'll start with the first one, looking at half-life. So what I've done is I've plopped down loads of atoms, and I'm only interested in the nucleus of the atom, because we're talking about nuclear decay, a change in the nucleus. And if you look on the right, you can choose your isotope, remembering that an isotope, well, 2 different isotopes of the same atom have different numbers of neutrons in the nuclei, but the same number of protons in the nuclei. So what I've got here, I've chosen the carbon-14, mainly because it ties quite nicely into the 4th tab on this little simulation. But I've chosen carbon-14, but you can try uranium-238 is the most common isotope of uranium found in the Earth. Naturally, and then we can pick one, we can make our own isotope, a custom one. It doesn't really matter. And what we've got on this little simulation, I hope it's coming through clear enough. We've got a pie chart, every physicist's worst chart. We don't like pie charts. And next to that will be a line graph, which is going to show on the y-axis the number of the carbon-14 nuclei, or in blue it will show the number of the nitrogen-14 nuclei, which is what carbon-14 decays into, and in the x-axis it's got time, and you can see that at some point after 5,000 years we've got this dotted line indicated half-life. So I'll just press play. Now the rules are the same. We don't know which nucleus is going to decay. Oh, that's the wrong sort of graph. It must be the other one I was looking for. My apologies. I haven't used the simulation in a while. We still can't predict which one. Okay, that one was the last one to decay there. We still can't predict which one will decay and when. It's still random. If you just look here, you've got all these nitrogen-14 that decayed early on and very few of them that decayed later. Well, that's because there were more carbon-14 initially. Let's just have a little look at that carbon-14, nitrogen-14 decay. Let's just have a little look at that before we move on to something else. So, I've got my pen here. Carbon-14. And the atomic number of carbon is 6. So carbon-14, is that sent? Yeah, that's on the screen. Carbon-14, we've already decided decays into nitrogen-14. Nitrogen-14. And if you have a look at your periodic table, you'll see nitrogen has an atomic number of 7. So what's happening here? What do we have to add to balance this equation, this radioactive decay? What we need to add is something that has no atomic mass, so I have to have a 0 there, and yet has -1 or -1 atomic number. And we can see that because 14 is equal to 14 plus 0, and 6 is equal to 7 plus -1 or -1. And so whatever goes here has to have -1. And I'm afraid this is just something you're going to have to try to memorize. That's an electron. We can indicate that with an E. But because the electron has come from the nucleus of the carbon-14 atom, we can indicate that with a beta. It's a beta particle. Just because there may be some A-level physics students watching this as well, and this, please, Finley, I know you're doing your IGCSE, so please you put your fingers in your ears for half a second. But if you're studying A-level, we also get a neutrino. Actually, it's an electron anti-neutrino emitted as well. But yes, ignore that if you're studying for your GCSE. So that's your carbon-14 decay. It's random. You don't know when it's going to happen. You don't know which one it's going to happen to. But that's the process. And what happens here is the carbon-14 is what we say is unstable. It's got too much mass. This number here is too big. It's not stable. And so this has to decay, losing some of its mass, or alternatively, gaining some positive charge in order to become more stable. And in this case, because it's neutron rich, we gain positive charge by chucking out some negative charge. The reason why we want this nice, especially with the smaller nuclei, this nice balance between the number of neutrons and protons, it's quite complicated. It's to do with nucleon energy levels, which you will not do until the first year of your degree in physics, so don't worry about it. We have to pick our battles. Okay, so that was our carbon-14 decay. And if I click on decay rates here, this is the one that's going to produce these beautiful graphs. Remember, this is live, so you can ask questions. This is going to produce these beautiful graphs. And I can plop, let's just pause it before I plop them down. I can plop lots and lots and lots of these down there. The more we have, the more accurate our graphs are going to be. And when I let go of this, it starts playing, and there we go. There's the graphs I was looking for. And you can see we've got 100% was carbon-14 initially, and none of it was nitrogen-14. And after what we call one half-life, actually this is slightly off, but that's the nature of this random, that's a consequence of this random behavior. So half-life, half, the definition of half-life is the time it takes for half of the carbon-14 nuclei to decay into nitrogen-14. And you can think about that in terms of mass as well, for half of the mass of carbon-14 to become nitrogen-14. The carbon doesn't vanish, it's all still there, it's just not carbon anymore, it's turned into nitrogen-14. And so there's your half-life. Now, after one half-life, we've got half of the carbon-14. So what do we have after two half-lives? We've now got a quarter of the carbon-14. And if we kept on playing this, after a third half-life, we would have an eighth of the carbon-14. And I've got some slides here, which I'm happy to send to you if you drop me a message on Facebook Messenger. Any of the resources I use here, I'm happy to share with you. So I've got some slides here that I use when I'm teaching this. And you can see this beautiful graph here with activity, where I've invented this new element. I don't know what you want to call it. Let's name it phenonium or something, in honor of the person who's interacting with me on YouTube Live at the moment. So we start at 10,000 becquerels. Right, we better define becquerels. Becquerels is a unit of radioactivity. It is the number of nuclei. So 1 becquerel means that we have one decay, so a difference in decay of 1 decay in 1 second. That's what 1 becquerel is. So we have 2 of the carbon-14 decaying, that means turning into nitrogen-14 in 1 second. We have 2 becquerels activity. In terms of equations, we can say that the activity, let's call it A, is equal to the difference in the number of nuclei of carbon-14 divided by some time step across which we measure that difference. And if we went back to that this simulation here, for example, that's what the gradient of this line was. The gradient of this line is the rate of change of carbon-14 nuclei, and that's what the activity is. Anytime you've got something divided by a difference in time, it's a rate. And that's measured in becquerels. Okay, I got distracted. So the activity is going down. It's going half, 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 half in each half-life. So let's just scroll down for a second. Let's just write this down. The number of nuclei we have after a certain number of half-lives, after one half-life, is going to be equal to half of the original number we had. So I hope you're happy with that notation, where n is just the number of radioactive nuclei we have after one half-life. This is after one half-life. And over here we've got the original. Now after two half-lives, we half it again. So we had this, a half times n times n0. Now we've got half of a half of n0, and that's after two half-lives. So this is one half-life, this is two half-lives. What have we got after three half-lives? After three half-lives, we've got our n is equal to a half of what we've got above, which is a half of a half of a half of n0. And so each time we just multiply by a half. Now when you multiply something by itself, you could say that you are squaring it. And if you multiply it by itself thrice, you can say you are cubing it. So a general equation for this would be that n after n half-lives, let's use a lowercase n for the number of half-lives, is equal to 1/2 to the power of n multiplied by the number of radioactive isotopes we had originally. Okay. Now, A-level physicists can use this equation. You can take the logarithm. You can then get that n from being a logarithm to not being a logarithm and use that to find what n equals for a given ratio of n to n0. Shouldn't have used capital N and lowercase n. I'm saying the letter n too many times. And if anyone wants me to go through that, because I see there are a few people watching live now, please go ahead, leave a comment below, and I'm happy to do that. But otherwise, I'm just going to move on. So that's what we can do with half-life. We can calculate after a given number of half-lives what our ratio is. In fact, I will mention this because I think it's worth doing. And Finley, I hope you can follow this okay. So if I know, for example, that the number of radioactive nuclei I've got, and I know how many I had originally, and I want to know how many half-lives has passed, then this is my equation here. I've just rearranged the equation on the right, dividing through by n0. Now, Finley, tell me, have you done laws of logs at all? Log to the base 10, log to the base e, that sort of thing. Not as far as I know. Okay. I mean, you wouldn't have done it in physics. You might have done it in maths. I'll show you a little trick. And if you don't want to use it, you don't have to. If you're not comfortable with this, just move on. It's fine. But this might help a little bit. Rather than just using trial and error to find out what n equals, you can do something a little bit more formal. So if I want to find out what n is, and I'll give a numerical example of this in a second, I can do, there's a button in a calculator called log, which means log to the base 10. Don't panic, it's complicated, but just know that it's a button on your calculator called log. And if you use that function, it will tell you what n log to the base 10 of a half. It will give you that. So if we go down like this, and there's some laws of logs now which will probably help any A-level students that are watching this later more than it will help you. So my apologies. If you're not enjoying this, Finley, you can ignore this as I carry on doing what I'm doing. So that's minus n log to the base 10 of 2. And then we can divide through. So we end up with n equals log to the base 10 of n0 minus log to the base 10 of nn divided by log to the base 10 of 2. Now, you can use that equation to find what n is. Actually, we usually use log to the base e, but it doesn't really matter. So if I give you an example, let's imagine I want to know how many half-lives have passed, and I've got some radioactive isotope where I originally had 10,000 nuclei, that's my N0, and now after some period of time, and I don't know what that period of time is, I've only got, I don't know, 1,000 So how do I find what that is? I get my calculator out. I type in log to the base 10 of my 10,000. And I minus log to the base 10 of my 1,000. And I divide through by log to the base 10 of 2. And I really hope I've got my maths right. Otherwise, this is going to be tremendously embarrassing. Calculator out. And once I've done this, Finley, I'll move on. So 10,000 log base 10. 1,000 log base 10, subtract. Why did I need a calculator for that? That was ridiculous. And 2 log to the base 10 and divide. Okay, that tells me it's 3.32 half-lives. So my number of half-lives is 3.32. And so if I know the half-life is a year, that's nearly 3 1/3 of a year, for example. Okay, let's move on then. So that was radioactive decay. At GCSE level, what do you need to know? You do need to know this. I'll just highlight it in green. You do need to know this. That's necessary. And you need to know this sort of process of 1 half-life, 2 half-lives, 3 half-lives, and you half it each time. You do need to know the definition of a becquerel. You do need to know what activity is. And all the simulations we've done so far. So let's load back onto here and get this thing out here. So carbon dating uses this principle because in the atmosphere there is carbon-14. Not a lot of it. There's carbon dioxide in the atmosphere. Again, not a lot of it, but don't worry, we're working hard as a species to increase the amount of carbon in the atmosphere. He says sarcastically. Yeah, so there's carbon in the atmosphere. And about 1 in 1.2 trillion of those carbon atoms in the atmosphere is carbon-14. That's formed because of bombardment of the atmosphere with radiation from the sun or cosmic radiation. It doesn't really matter. We've got carbon-14 in the atmosphere. And we know how much that should be. The sun has been pumping out the same radiation for billions of years. Our atmosphere composition hasn't changed that much. So we know over a long period of time that the proportion of carbon-14 to carbon-12 in the atmosphere should be constant. And in fact, here we can see we've got the graph. It's very, very small text. I can barely see it on my screen, and yours is recorded through a video, so you probably can see it even less than me. You can see here it's sort of 1.3 times 10 to the negative 12. That's the ratio of carbon-14 to carbon-12. So there's not a lot of carbon-14. But I'll use the percentage. So this is 100% of what there is naturally occurring in the atmosphere. It doesn't mean that 100% of the carbon is carbon-14. It just means that's the normal level. Now I'm going to plant a tree, and I'm going to detect by looking at the activity, the radioactivity of that tree. I'm going to detect and work out how much carbon-14 there is in that tree. The tree, while it's alive, is going to be undergoing photosynthesis and respiration. So it's going to be constantly recycling the carbon-14 it's got within it with the carbon-14 outside. It's going to be constantly cycling that. Through photosynthesis, it's going to be taking carbon in, and so bringing new carbon-14 from the atmosphere in. And through respiration, it's going to be releasing carbon dioxide, and therefore releasing carbon and carbon-14. And so, while the tree is alive, we would expect the proportion of carbon-14 to carbon-12 in the tree to be the same as in the air. Again, please ask questions or stop, or give me a virtual "huh" if you're not following. So that's the first step. So let's plant the tree. Now, so the tree is alive and our probe is showing 100%. That's the amount of carbon-14 that is in the atmosphere is also in that tree. Now, the tree has died. It's a nice old tree, 1,500 years old, but the tree is now dead. And when it dies, those processes, that respiration and photosynthesis, stop. And because they stop, and the tree's dead, the carbon-14 that was in that tree is now trapped there. It can't be recycled. It's trapped in that tree. And so over time, that amount of carbon-14 is going to drop because the carbon-14 will decay. In every half-life, sort of 5,400, whatever it is, 5,400 odd years, every half-life, the amount of carbon-14 has halved compared to the amount in the atmosphere. So if we now watch this tree closely, there we go, we can see over time the amount of carbon-14 is dropping. And so if we come, let's say we turn up and we find an old boat in a peat bog somewhere, and we find this boat and we think, oh, I wonder how old this boat is. And we take a little sample of wood from the boat, we take it back to the lab and we isolate the carbon. You could do that chemically, and then once you've got that carbon, you get exact amount of that massive carbon. You think, right, okay, now I know this massive carbon, I know the proportion of that should be carbon-14. So you detect the radioactivity of it with a probe, which, you know, using a Geiger counter probably, and then we go, oh no, it's got less than what's in the atmosphere. By what proportion? And then we can use a graph like this to say, right, well, this is how old the tree, well, how long ago the tree died. And of course it's impossible for the tree to have been made into a boat while it was alive, and so we know sort of the minimum age of the boat, and that's called carbon dating, or radioactive dating. Very common thing that is done. It does have limitations. You can see after a few half-lives the amount of carbon-14 is so small it becomes difficult to discern it from background radiation. And there's a little game here. If you want to test yourself, you can play this little game. Download this later and play it. So this is 97.4. I can scroll this across to 97.4, which is there. 216 years. If I type in 216, oh, a nice smiley face. Look at that, I'm correct. And if I go down to the next one, where is it? Let's move the probe to there. When did that human die? So 76.6. Let's put this on 76.6, 2193, 2193, bing, and so on. And if you find things that don't, things like this, a rock, there are two things you can do. You can either, well, maybe not the rock, it's a bit too far underground. But if you find things that don't have any carbon in them, but they're the same depth in the ground and surrounded by things that do, you can carbon date those and then infer the date of the thing that doesn't have carbon, or you can use some other radioactive isotope. And so uranium naturally occurs in the Earth as well. So that's pretty much everything you need to know about half-life radioactivity. My friend, I didn't get on to nuclear physics. You mentioned that you wanted me to look at fission and fusion. I'm happy to do that now, but I'm very mindful of the fact that this is the half an hour that I promised, and you might be getting a bit tired of the sound of my voice. So do let me know. If you want to talk a little bit about fission and fusion, I'm happy to do that now. Might as well, while we're in the mood for it. Just comment below if that's the case. But if you don't, if you say, no, do you know what, that's enough, then we can stop now. Just waiting for a reply. 7-second delay. Of course, the other possibility is that Finley, who I've been interacting with, is gone, and I'm waiting for him to reply, and he's not there. That's possible. 15-30 minutes for me to explain fission and fusion. That's good, right? Yeah, great. So I'll carry on for just a little bit. I think it's worth doing. So fission and fusion. I'm going to have to go onto the FET website now to download another little simulation. So let me go on here. Yep, that's all there. So if I go into simulations and physics, this is how you can find these, by the way. And there's one that's called fission, I think is called, something unimaginative like that, hopefully. No? Okay. It's called nuclear reactor, maybe. That'll be under N. Nuclear fission, there we go. And you can download this. Some of these are HTML5 files, so they play within the browser. Some of them, like this one, isn't. You'll have to, let's just go on to this for a second. You'll have to download the file, and it's a Java file, so you'll have to have something to run the Java file. It's all a little bit of a nuisance, but they're good. They're worth the effort. So that should have loaded now. Yep. Okay, so let's talk a little bit about fission and fusion. Let's start with fission. So here we've got an energy diagram. And it looks complicated, but it really doesn't need to be. What we've got here is a graph of potential energy. And if you want to visualize it, think of gravitational potential energy. I need to emphasize it's got nothing to do with gravitational potential energy, but it's a helpful way to visualize it because we are so used to gravity that we can talk about some complicated nuclear things in those terms and help understand what's going on. So with gravitational potential energy, I hope you remember that the higher up you are, the more gravitational potential energy you are. And so with this graph of potential energy, this is a nuclear potential energy. What I want you to imagine is this is a hill. And in fact, we do refer to these things as energy hills and energy valleys and things, even at degree level. That's a normal sort of terminology. So we've got this energy hill, and at the top there's a bit of a dip. And this is where our atom sits, our nucleus sits quite comfortably there. And I hope you can see that this nucleus cannot possibly get out. It's got to sit there. It cannot possibly end up at the bottom of this hill. But everything wants to reduce its energy. That's a principle in physics, that everything is trying to reduce its energy. Try and think which one it is. I think it's the second law of thermodynamics. Yeah, I think it's the second law of thermodynamics. Or maybe it's the third law. I'll have to look that up. So this nucleus wants to reduce its energy. It can't. It's sat there. But if I give it a little bit more mass, it goes up a little bit more, becomes unstable, and then can decay. Now, at A level, you'll learn about quantum tunneling, and actually it is possible for that nucleus to decay by tunneling through this barrier. The probability of that is very low, and that's why uranium-235 has such a long half-life. The probability of decay is very low. But I can increase the probability of decay of uranium-235 by making it uranium-236. Now, for very complicated reasons to do with, again, energy levels within the nucleus, which you don't have to know about, even at A level, for very complicated reasons, uranium-236 is a lot less stable than uranium-235 and than uranium-238. So uranium-236 will exist in that very highly excited state for a fraction of a second. It'll almost instantly decay. And because it's so unstable, it doesn't decay by just spitting out an alpha particle or something like that. It completely crumbles apart. It's catastrophic. It blasts apart into these two daughter nuclei. And so we call this an induced fission. We induce fission by making the nucleus absorb a neutron. And there's some key words we have to be careful of. We can't say, oh yes, the neutron collides with the nucleus. We have to say the nucleus absorbs the neutron. Just the nucleus, the neutron colliding with the nucleus is not enough. The neutron has to be absorbed by the nucleus for the nucleus to become uranium-236, and that is so unstable it will decay very quickly. Now that decay, I don't know if you noticed, so watch closely, that decay also emits a few spare neutrons. It's such a violent decay that those daughter nuclei, which have roughly a 1/3, 2/3 balance of the mass, those two daughter nuclei that are left, as they blast apart, a few neutrons also separate. And those neutrons, when they separate, actually separate and they travel very fast, that's important for something that's going to come later. So here I'm going to have some uranium-238. Uranium-235. Let's put lots of uranium-235. And what I'm going to do is I'm going to introduce a neutron, which is going to be absorbed by one of these uranium-235. Now, when that uranium-235 decays and emits its daughter nuclei, which will move, they will move quickly because if they've got this increased kinetic energy. Why do they have that increased kinetic energy? Because they're losing gravitational potential energy as they move down this graph, and so that's why they gain kinetic energy. Just like when you drop something, as it falls, it loses gravitational potential energy and hence gains kinetic energy. It's the same thing with this. So when these two daughter nuclei split apart, they have lots of kinetic energy, but so do the neutrons. And the neutrons can then be absorbed by... Hello, that didn't work. Let's try this again. The neutrons can then be absorbed by... Oh, I've paused it, that's why. Can then be absorbed by the other nuclei, the other uranium-235 nuclei. And we have this catastrophic chain reaction. So let's try that again. Watch closely. I introduced one neutron, it was absorbed, and because each nucleus then emitted two or three neutrons, I mean, that one up there didn't manage to fission. Lucky it. Have I managed to hit it? Come on. Ah, close. Okay, so because there's two or three neutrons being emitted by each fission, this is not a one-to-one sort of thing. This isn't a stable reaction. This is the sort of thing you might have intentionally if you were designing a nuclear weapon, which of course I do not endorse. Nuclear weapons are horrible things. Let's just move that into the middle of the screen a bit better. There we are. Anyway, so there's that. Now, what if I had uranium-238? So here's uranium-238. This is the most common isotope of uranium that is found in the Earth naturally, uranium-238. And it's more common because it's more stable. And in fact, look, uranium has absorbed a neutron and nothing's happened. It's become uranium-239. Now, uranium-239 will decay, and it will decay actually into plutonium. And then plutonium can absorb neutrons and things. But uranium-238 and plutonium they're sort of reactor poisons. They absorb these neutrons but don't actually emit straight away more neutrons. And so uranium-238 and plutonium-239, these are your reactor poisons. We don't want them. Actually, we do. And the problem at Chernobyl was they didn't have enough reactor poisons, or at least they didn't understand the delicate balance between poisons and fuels well enough. So if we have a mixture of them, let's just get a mixture of these things. Can I get the neutron through? No, I can't get it through. Let's reset them all. And there's some more of these near the beginning. So what we can do is we can try and get a balance of this fissionable uranium, this uranium-235, and this uranium-238, which does not fission, or at least it doesn't fission straight away, and try to get a reaction that takes longer. So what enriching uranium is getting uranium-235 and uranium-238 that occur naturally and shifting the balance. So removing some of the uranium-238 to increase the proportion of uranium-235. And we do that, but not so much that what we're left with is too much uranium-235 for reasons that you've just seen. Uranium-235 is tremendously unstable. So we need some uranium-238 there, otherwise it's a very, very dangerous bomb. It's also quite hard to enrich it, actually. So we only have to increase the proportion of uranium-235 by a little bit. Okay, so this is a reactor core, a fission reactor core. And in this reactor core, we have something called a control rod. And the control rod will absorb neutrons. So what I've got in this reactor is just uranium-235. That's obviously not reality. It's just a simple picture. And if I press fire neutron, I introduce a neutron into this. Am I being unlucky? There we are. Then what you'll see is very quickly that reaction is going to increase in rate. It's going to get faster and faster and faster because each of these decays releases 3 neutrons, and each neutron then is absorbed by a uranium-235 nucleus, which then decays, releasing 3 more neutrons. So you get from 1 neutron, we then get 3, then we get 9, then we get 27, and so on and so on. So the reaction rate is tremendously unstable, and you can see we've got a certain amount of energy out, good news for us, but the power output, we couldn't really do much with it. If you look at the power output, imagine that we're trying to run a nuclear reactor to power some homes, and we press the go button, the power output shoots up and then shoots back down again. So we're on the phone to everyone saying, okay, you can't turn your kettle on yet, we need to shoot a neutron in, and then you'll have 5 seconds to boil your kettle, and then we'll be out of juice again. Obviously that's not what happens. So we need to control this rate of reaction. And the way we do that is by trying to absorb 2 out of the 3 neutrons. And so it becomes a delicate game of insert and then retract, and then insert when the reaction rate gets too high, then retract, then insert, then retract, then insert, and trying to keep these to keep that power output as stable as you can. It's a fun game. It's hard to do. It's gone down a bit. Then put it back in again. It's going up a bit too far, and then put it down again. Now it's going up a bit too quickly. Put it in again, and so on. So it's a delicate game that you play. So those control rods, what do? They absorb neutrons. Well, you make them out of neutron absorbers, like boron. Boric acid is something we can use for that. So what have we got in our fission reactor core? We've got nuclear fuel. And our nuclear fuel is going to be uranium, mostly uranium-238, but it's the uranium-235 that we want to do the fission. We've got control rods. And the control rods, usually made out of something like boron, cadmium, that sort of thing, boron, they're going to absorb neutrons. And we want to absorb... I'll write this down here. These absorb neutrons. And these emit neutrons, I suppose, when they fission. They usually emit 2 or 3 neutrons. 2 or 3 neutrons. I wrote 3 or 3. 2 or 3 neutrons. So we've got those 2 components. But that's not all. Because the reactor's purpose is to generate electricity. That's what it's for. And so to generate electricity, what we have is a reactor design that looks a bit like this. Is that on the screen okay there? Looks okay. So we've got this reactor design where we've got in the middle here, and you can find this picture on Wikipedia, that's where I stole it from. In the middle here, we've got our fuel and our control rods. In the containment structure, that's the reactor core, and we use that to heat water. And what's actually heating the water are these fast-moving neutrons. These fast-moving neutrons, as they collide with atoms of molecules of water, they slow down a bit. And when they slow down a bit, that's because they transfer kinetic energy to the molecules of water. And those molecules of water, when they gain kinetic energy, they're moving faster. And that's what heat is, how quickly these things are moving around. So we heat up the water. So water in this containment structure is the coolant. And the purpose of the coolant is to extract heat from the core. Now in this reactor design, we've actually got 3 water circuits. The first water circuit here is all contaminated because the water is in contact with this radioactive fuel. Then we've got the second water circuit, and we pump this cold water in, which boils because we've got this heat exchanger here. Heat from the primary water circuit is conducted through into the secondary water circuit. That boils the water, making steam. Steam drives the turbine, and then we need to cool that steam down to make it water again. So we have a tertiary, or a third water circuit, drawing water from a reservoir or from the sea or from a river or a big lake, drawing that water in and using that cooler water to condense the steam. And you've got to have these 3 circuits, because if there's a leak in this primary pipe, all of the secondary circuit of water will become contaminated and need to be flushed away and stored. Now, if there was a leak between the second and the third circuit, not a big deal. If there's a leak between the first and the second circuit, big deal. We're going to have to pull all that water out and store it. If we didn't have that middle circuit, then a leak between the first and the great outdoors would mean we're releasing radioactive waste into our water, and that would be bad. That would be bad news indeed. So this generator, the turbine pushing a generator generating electricity is the standard for all sorts of thermal what do you call them? Power stations, thermal power stations. So we've got coolant. We better write that down. Coolant. And a very common coolant is water, although advanced gas-cooled reactors use carbon dioxide. And the idea of that is to extract heat from the core. That cools the core down a little bit. And there's one more component, because it turns out that the neutrons, when they first are emitted by the fission reaction, are moving too fast to be absorbed by uranium-235. You have to slow them down a little bit. And those fast neutrons that are emitted, those fission neutrons, have to be slowed down by something we call a moderator. Moderator. That's bad handwriting. Moderator. Now, actually, in most reactors, most modern reactor designs, we use water for the moderator as well. So the coolant is the moderator. But that wasn't always the case. So the idea of the moderator is it's got to slow neutrons down. And it does that by the neutrons colliding with the atoms of the moderator. And there's usually 50 collisions or so. With the moderator, these neutrons collide 50 odd times, like a pinball bouncing around the table, until it's slow enough to then be absorbed by uranium-235, which will then fission, releasing 3 neutrons. And then 2 of those get absorbed by the control rods, and the other one goes bing, 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 gets slowed down by the moderator. And because the moderator in most modern reactors is the coolant, then that energy gets carried away by that water. And that's the gist of how a nuclear fission reactor works. Now, I will very quickly talk about nuclear fusion. If you've got any questions, do ask. You said you've got about 15 to 30 minutes, and I've spent 20 of them. So hopefully you can tolerate me for just a few more moments, just so we can talk about classic diagram of a chain reaction. Classic. Every exam, every year asks you to fill in the blanks. Obviously, you don't need to know each of the isotopes, but the idea that we've got these neutrons that are released, and we really want one neutron to be absorbed by one uranium-235 nucleus. You'll see these are labelled uranium-236. That's because they've already absorbed that neutron. And look at the mess. We can make cesium, rubidium, strontium, xenon. We can make all sorts of isotopes as waste. And the isotopes that are waste can react chemically. Some of them are going to be strontium in particular, cesium. These are radioactive isotopes. So what do we do with that waste? We put it in a barrel, bury it underground, and hope no one digs it up. What a horrible species we are. Right, let's scroll down a bit further. So this is the gist of nuclear fusion. In nuclear fission, we split apart big atoms and it released energy. In nuclear fusion, we join together smaller atoms. We need to be careful here. We join together smaller nuclei. If you say atoms, you lose marks in exams. We join together smaller nuclei to form bigger nuclei, and that also releases energy. You can fuse larger nuclei together, but it takes more energy to do that than it releases. So fusion reactors will fuse things like hydrogen or isotopes of hydrogen, like deuterium, which you can see here is deuterium there. We'll fuse those into helium, and you can see helium fuses with helium to form helium. In this particular fusion reaction, which happens in the sun, we've got 6 hydrogens going in, 1, 2, 3, 4, 5, 6, and what comes out is 1 helium, 2 hydrogens, and they can go on to further fuse, and some gamma rays, that's energy, and some neutrinos, remember that's A level, don't worry about that, and some positrons, that's antimatter, again, don't worry about that, that's A level. So that fusion reaction happens in the sun. Reason why it only really happens in the sun naturally, is because the nucleus of a hydrogen atom, so that's just 1 proton, which is positively charged, repels the nucleus of the other hydrogen atom, which is another proton. And that repulsion gets really strong when they get close together. But they've got to be within a couple of femtometers within that range in order to fuse, forcing one of the protons to turn into a neutron by emitting a positron. And that fusion, that can't happen unless these 2 protons are close enough together. Now, getting them close enough together is a bit of a challenge because of that what we call the Coulomb Barrier, that electrostatic repulsion. They're both positively charged, they repel each other. But it turns out if you throw them at each other with enough kinetic energy, then that force, that repulsive force, which is removing the kinetic energy as they move towards each other, if you've got enough kinetic energy, then they can get close enough together. How do you give things kinetic energy? You heat them up. So in the sun, in the core of the sun, it's hot enough for this fusion to happen. And we're trying to produce those sorts of very hot environments on Earth. And that's the old tokamak design here. So this tokamak design, sorry, some of the words are being eclipsed by my face. Let me move my face down there for a moment. There we go. Okay, so this tokamak design is, well, it's currently being built, and it should be finished very soon. I think they might have actually finished building it, but they're not ready to test it yet. Hoping that it's going to generate much more energy than it takes to run it, but only for a very small fraction of time. The problem is, the technology costs billions to develop. And if you go up to a government and say, I'd like some billions, please, to develop a technology, they're going to say, where's your proof of concept? I'm not going to throw money at a project that's not going to work. So they'll say, here's a little bit of money, here's 100,000, here's $1 million. Go build something that shows some ideas. Tell me what you want to do with the next part of the money, and we'll give you some more. And so that process of applying for grants, getting grants, doing something, applying for more grants, that takes time. We've been working on this for nearly 100 years. Well, no, not nearly 100 years. But it will be 100 years from when we started working on it till we actually get this working and on a commercial scale. The advantage of this is the fuel is hydrogen. We've got a lot of hydrogen on Earth. It's among the most abundant, well, it is the most abundant element in the universe. So we've got loads of hydrogen. The other plus side is that there's very little radioactive waste. There is some, because we will get positrons, for example, and gamma rays bombarding the containment structure, which means that may become radioactive. And so there is some radioactive waste, but far less than fission reactors. And the big advantage from my personal point of view, me being a pacifist, is you can't make bombs out of the waste products from this, whereas you can with a fission reactor. So for me, this is where is it now? It's up there somewhere on my camera. This technology is I really hope the future. Right, that is probably as much as my voice as you can tolerate. So thank you very much for. I'm just going to pop a little advert there. Thank you very much for coming along and interacting as well. That was really good to get those sorts of interactions. You didn't ask very many questions, so next time maybe do bring a few questions. That's worth doing. You've seen I've got this whiteboard. If you want to work through some maths problems, I'm happy to do so. We can work through things together. And this is open to everyone. This is tutoring for everyone, but while no one really knows about this, you have the advantage. If you ask me questions in advance, then I can get things loaded up ready, all these simulations and things that are appropriate. And if there are any resources that you want that I've got, please just ask. I've got stuff coming out my ears. I've made various drills and presentations. This one here I made for my school, which is the entire GCSE that we teach. All in one document. You can probably see there it's 335 pages. It's quite long. Okay. Well, it's pretty much 11 o'clock. I've been talking for an hour now, so I hope that was useful. Please do like, subscribe, share with your friends, and I'll see you next week. Stay safe.